So I'm starting off the talk with just kind of an overview of two of the main use cases that we have for LTP. So as we were talking a little bit yesterday, we've been focused on an ISS demonstration with Illumity and LCRD that is featuring a high rate optical link. So this is a large scale platform, and HDTN was deployed on a commercial laptop. And we were looking at gigabit per second rates with a bidirectional link. So it was 155 megabits forward and 1.2 gigabits per second return. And there was also a significant round trip time of 4 seconds. So this was a system where we have, capable of supporting multiple payloads and then also multiple ground stations. So you can see in our picture here, and actually it's a video, but it's not, I don't think the video is playing. But either way, basically we have from the ISS the link to LCRD and then LCRD to any of these 3 ground stations. So it has multiple source and multiple destination. And another feature of this was that the software is able to be updated, after it was launched. It was kind of accessible relatively to the operators, so you can reconfigure it and update it. So we were focused on demonstrating the high-speed gateway, and also all of the tests that we did used LTP, and we were focused on BPv6 and BPv7 with BPSec and multimedia streaming. So the second use case is kind of the opposite, where we're looking at a very small platform. So this is the TechEdSat 11 CubeSat that we recently launched. So this is a small embedded platform. And an important feature of this is that the radio itself is very limited. So for downlink, it simply has a transmit-only unidirectional S-band radio that only supports about 1 megabit per second. And then it has a command interface that is using Iridium short burst modem. So it's only very small packets that are like 200 bytes, and that's strictly for commanding. And also, once the software is on the CubeSat and it's integrated and deployed, it's impossible to update the software, and there is only very limited chance to maybe do a small bit of tuning parameters. So this is, just a small payload. And for this case, another feature of it is that we're using kind of a custom communication pipeline. So we're using kind of the space protocols for CCSCS, NCAP, and AOS. And there's a very kind of non-networked kind of architecture, where versus the Illumity, we had an extensive ground network, we had the onboard network. So it was almost kind of like working in your terrestrial network, kind of with Ethernet, whereas this is a very specific protocol stack. And so for this case, we are actually not using LTP. We're using forward error correction. So the pipeline, COM pipeline, has Reed-Solomon, but we also have an FEC bundled protocol application that we're going to be testing. So for HDTN, since this talk is about the performance and benchmarking, the important features are the message bus architecture. And we also have, for all of our main modules here, we can run them in a distributed or single process mode. So they can actually have ingress and egress and storage all completely on separate machines. And we also try to avoid semaphore and mutex on shared memory and avoid copying, and we kind of stick with an asynchronous mode of operation. So we've evaluated LTP in multiple environments. So I've talked about the LCRD experiment, and we're also working on an optical comm experiment with our PC-12 aircraft that's using a commercial optical terminal. We also have a software-defined radio lab that uses Cesium Astro SDR FlatSat. It's a flight-like radio. And we also have a LunaNet test bed that is multiple Raspberry Pis, and we use the Netropy network emulator to add delays similar to the lunar environment. And then finally, Fred has tested our LTP in his own 100 gigabit per second test bed, and he's going to get into a lot of detail on that. So for LTP, there are really some challenges, and this picture here is our outduct configuration for HDTN. And you can see there's a lot of parameters to configure. And so this makes it kind of prone to errors just from operators being confused on parameters. And if it's not tuned properly, you can actually have poor performance. We're also going through the CCSDS specification, And it's actually difficult to derive requirements from the specification just due to some of the complexity of it and some of the terminology. And the other kind of problem is that it still needs two-way communication. So even though it's intended to be operated over two different channels, like I was showing for our CubeSat, in some cases it may not be possible, or the links may be such that this really degrades performance. So we're looking to try some parameterized benchmarking and analysis, and Fred has done some of that. We're also interested in looking at a trade study between LTP by itself versus bundle protocol with custody transfer, and also investigating new protocols like the HPRP, which is trying to address some of the complexity of LTP. And then another possibility would be forward error correction, which we're getting into in this talk, and further refining the protocol specification. And with that, I'll hand it over to Fred.
Thank you. Thanks, Rachel. So with these high data rate links that we're going to be putting into space application, there's going to be very few paths available because it's very expensive to put equipment up in space. So it's very important that we get the most performance possible out of the paths that are going to be available. And we've found that packet sizes very much determine the performance of these DTN implementations. So when we run LTP UDP over UDP-IP, we find that most internet and DTN links configure a maximum transmission unit of 1,500 bytes. And that means that's the largest size packet that the link can handle. The smallest link MTU in the path determines the path MTU. And transport layer protocols like TCP, QUIC, LTP, and others often limit their packet sizes to no larger than the path MTU. To go to larger sizes, you need to use a service called IP fragmentation, but there have been many studies that have considered IP fragmentation to be harmful. A study back in 1987, a newer study that the IETF conducted in 2020 called IP fragmentation considered fragile. And so now the IETF is instead recommending to use path MTU discovery instead of fragmentation wherever possible. But the problem with path MTU discovery is it depends on a message coming back from the network called a packet too big, but these messages might be lost or spoofed. So the packet too bigs always indicate packet loss. The source has to back off to using smaller packets for a long period of time before trying again. And that's not adaptive. You're always stuck in small packet sizes. Discovering larger MTUs over arbitrary internet paths is difficult using legacy path MTU discoveries, but the IETF has invented some new ways of doing it. One is using active probing approaches for TCP and UDP, and a new approach is using passive hop-by-hop measurements, which is this IETF RFC 9268. So because of path MTU discovery shortcomings, it often causes transport protocols to use smaller segment sizes. The small segment sizes can cause performance bottlenecks at the operating system call interface, since only a small amount of data is copied per system call. So there's a service called generic segment receive offload that concatenates multiple smaller segments into a larger buffer to amortize the data copy across the system call interface. So the source operating system would fragment the large GSO buffer into smaller whole packets for transmission. The destination OS reassembles packets into a larger generic receive offload buffer for transport protocol delivery. So that's the way you can do a kind of a poor man's fragmentation reassembly. Now let's consider the way the DTN protocol layering works. The DTN bundle protocol introduces a new layer in the architecture that's below the applications but above the transport protocols. And the Licklider transmission protocol is a transport protocol convergence layer for bundle protocol. You can see them in the blue in the left-hand diagram. LTP breaks bundles into segments for transmission, and we found that segment size very much affects performance. Now, in the ION implementation, we have this LTP meter that governs how buffers are transformed into segments for transmission. The LTP meter initializes a session buffer and gives the buffer open semaphore, waits for the buffer close semaphore to indicate that the session buffer is full, then segments the entire buffer into segments of managed MTU size with fragmentation in consideration, and appends all the segments to segment queue for immediate transmission, then gives a segment in queued semaphore. That's the way segmentation works in LTP, in ION. So LTP performance, we implemented GSO, GRO, and ION DTN LTP, but we saw no performance benefit from doing that. So the system call interface, at least in ION, is not a bottleneck. We experimented with larger ION LTP segment sizes that showed dramatic performance increases, even though it was engaged in IP fragmentation. And we found that larger HDTN LTP segment sizes also showed significant increases. So we now know that for two popular DTN LTP implementations, increasing the LTP segment size directly increases performance even when IP fragmentation is engaged. And this mirrors earlier internet services such as NFS over UDP that saw greater performance using larger segment sizes with IP fragmentation. So in our performance testbed in Boeing, we have two Dell Precision workstations running Ubuntu with 12th generation Intel Core i7 processors and 32 gigabits of memory. The key thing that we have here is Intel 100 gigabit per second Ethernet network interface cards. They're connected point to point with the Cat6 Ethernet cable. The NICs can accommodate MTU configurations up to 9702 octets, and we use 1500, 4500, and 9702 octet MTU tests in our settings in our tests. So first, with the NIC set to a 1500 MTU, we found that when we sent using HDTN LTP segments up to 1400 bytes, we were getting 9.1 gigabits per second. But then what we did was we boosted the segment size to larger sizes. And we found that when we increased the segment size to 16K bytes, which incurs IP fragmentation, we get all the way up to 18.12 gigabits per second. That's a 99% increase, even though we're engaged in IP fragmentation. So this is very much showing that segment size has a great bearing on performance in HDTN LTP. And then when we go all the way out to the right, we see that with 64K segment sizes, we get to 20.62 gigabits per second for a 127% increase over when we're not using fragmentation. So that magenta curve that you see there, all that space that's above the dotted line is a gain that we get for engaging IP fragmentation with larger segment sizes. By the way, the other two charts, graphs here, the green and the blue, are iPerf using TCP, which is the blue, and UDP with IP fragmentation, which is the green. So then what we did was we boosted the Ethernet MTUs to 4,500 bytes, and that says that that's the largest packet that can go over the Ethernets before you require fragmentation. And when we did that, we saw that the HDTN performance boosted all the way up to 20.432 gigabits per second using 4,400 byte segments. We then engaged IP fragmentation by going to larger segment sizes, and you can see the magenta curve still provides a performance gain, but not as dramatic as what it was when we had smaller MTU sizes. So we got to 25.89 gigabits per second with 16K segments, and all the way up to 27.9 gigabits per second with 64K segments. So we're 37% increase. Then finally, we boosted the Ethernet MTU up to 9702 bytes, and again, HDTN showed a dramatic increase for using segment sizes that are no larger than the MTU, 29 gigabits per second. That's just by boosting the segment size up to 9702. And then for the larger segment sizes, IP fragmentation showed only a smaller benefit, but did show significant benefit nonetheless, up to the point we get to 32 gigabits per second out to 64K segment size. So what we take away from this is that HDTN LTP performance implications are that the HDTN engages the network at high utilization. So we believe it makes a good fit for high data rate DTN relay over laser links, where we need to get the maximum throughput out of our expensive links. For nominal path MTUs like 1500 bytes, performance is more than double with larger LTP segment sizes that engage IP fragmentation. For larger path MTUs, the 4500 and the 9702, the larger LTP segment sizes provide significant performance gains, and IP fragmentation still provides considerable gains for larger MTUs. What this shows is that HDTN might benefit from going to jumbo path MTUs that are larger than 9702, and I'll talk about that a little bit later. HDTN may also benefit from GSO GRO, which is something that we need to investigate in the future as we go into our studies in more depth. Now we took a look at ION. Now we found that with ION, we did not have a performance correlation for the MTU size. We had the same curve for 1500 byte MTU as we did for 9702 MTU. So we see that over on the far left, with 1400 byte segments, ION is only performing at 154 megabits per second. But when we boost to 16K bytes and engage IP fragmentation, we get all the way up to 1.2 gigabits per second for a 740% increase. And when we go over the way over to the right, we see that we get to 3.877 gigabits per second for a factor of 25 greater just by increasing the segment size. So LTP is very much performance bound by the segment size, and without as much dependence on the underlying path MTU. So we see that ion DTN does not fully engage the network in nominal segment sizes, but based on a lightweight multiprocessing architecture. And so we think it would be a good fit for lower end links of end systems such as spacecraft. The performance profile is identical at all path MTUs up to 9702. We found that increasing LTP segment size produces a linear performance gain for all sizes when IP fragmentation is fully engaged. And with IP fragmentation, the largest segment size you can use is 64K bytes. If you wanted to go larger than 64K bytes, you'd have to send what we call super jumbos. And we think ion will find significant performance gains at super jumbo segment sizes. For example, a 256K byte packet, 512K byte, 1 megabyte, 10 megabytes. We can go as large as 4 gigabyte packets, making the packet size be identical to the bundle size potentially. So this is requiring a new service called jumbograms, and I'll talk about that more in a bit. So what are the things about IP fragmentation that we need to consider? For IPv4, IPv4 includes only a 16-bit identification, and it can wrap at even moderate data rates, which could potentially cause reassembly errors. That's corruption. There's an RFC that talks about this, and that's bad. So we don't want to drive IPv4 fragmentation at high data rates if we can help it. IP version 6 includes a 32-bit identification field, but even this length is still too small if the starting sequence number is going to be reset frequently. We have defined something in the IETF called the IPv6 extended fragment header that includes a 64K bit identification field, and that addresses all these issues. And that's going to be included in what we call the Omni interface, which can do fragmentation of a layer below IP. IP fragmentation is only used for segment sizes up to 64K bytes. The larger sizes would require IP parcels or advanced jumbos. Now, dealing with fragment loss and reassembly congestion, the destination would send a fragmentation report soft error to the source. The source can then adaptively increase or decrease the size of its packets. This supports adaptive packet sizing on a per flow granularity. So some of the criticisms about IP fragmentation were that if you lose a fragment, it's terrible. Well, no, it's not really terrible if you are adaptive. Just simply start sending smaller packets and grow to larger packets in the future if you can. So it becomes a sliding window of packet sizes based on network conditions. Now, what about these IP parcels and advanced jumbos? Some transport protocols may benefit from segment sizes that exceed 64 KB where we can't use IP fragmentation. The peers can use IP parcels and advanced jumbos over paths that support them. How large can they be? IP parcels includes up to 64 kilobyte segments for a total of 4 megabytes possible with parcels. Advanced jumbos include a single segment size up to as large as 4 gigabytes. Well, what does that do to integrity? Well, with links in the internet, the CRC32 frame check sequence is only used for data sets up to about 9K bytes. So what we would do is use the link layer CRC for the headers only and employ a much stronger end-to-end integrity check. Well, what if we get corruption when we send these large things? That's where we want to engage forward error correction. The sender would encode with forward error correction, the receiver decodes with forward error correction, and then the end-to-end integrity check determines whether the FEC was successful. By doing this, we can send large packets without having to retransmit even if we had just a couple bits of corruption because the forward error correction would correct that corruption. So the one thing about these larger packet sizes is when you bet big and lose, you lose big. So you want to bet big only when you know you're not very likely to lose. Only send these large packets when you know network conditions are favorable for them or when forward error correction can correct any errors. So segment size considerations. The segment size determines the retransmission unit. Loss of a single fragment requires retransmission of the whole segment. GSO and GRO employ MTU-sized segments even if the path MTU is small, so that loss of a single GSO packet requires retransmission of only the single packet. So that means the lost unit is small and the retransmission unit is small. So the pragmatic approach would be to use large segments only when the loss probability is small, to use forward error correction to repair damaged segments whenever possible, and to be adaptive to accommodate changing network conditions. The choice between GSO, GRO, and IP fragmentation can also be adaptive according to network conditions. Both tools are going to be useful. So now future work, did you want to touch on that, Rachel?
I can do so. So what we're looking at for the forward error correction would be, we're going to test for the Tech Ed Set 11, we're going to try with and without our forward error correction. And one of the things we're hoping that that will address is if we can possibly have a way in which we're not needing to have acknowledgements, which could really be a performance boost for cases where you have a long round trip time. So that's one of the things we're interested to collaborate on. We're also interested in LTP analysis continuing between GRC and Boeing. And we're also, for our PC-12 experiments that are going on throughout this month, we're going to be trying some LTP parameter tuning, and we're going to look to see if we can reproduce some of the, increasing the segment size to reproduce Fred's work in the flight experiments. And we plan to also investigate HPRP and custody transfer versus LTP.
Then the other thing we want to look at is the send end message and receive end message that are already implemented in HDTN, see if we can get some performance gain from them, but then also implement GSO and GRO in HDTN. What we'd expect to see there is a profile similar to IP fragmentation, but we wouldn't get as much gain as IP fragmentation because we'd be sending more headers with GSO and GRO than we'd be sending with IP fragmentation. And then finally, as Rachel said, incorporating forward error correction in larger packet sizes. That's going to get us to a place where we can send these larger packets over longer distance links and have them be accepted there without being lost due to corruption because of the forward error correction. I think that's going to be it there, Rachel. This is just the collaboration and references. This is the team that was engaged in this study. And we have an earlier version of this work that's published in the Asia Pacific Network Information Center blog. And there's a link to the document if you want to go there and look at the document.
Okay, thank you, Fred. Thank you. Well, very happy to see HPRP mentioned. We definitely should have a talk about this sometime not too far in the future. Questions, Alberto?
Thank you. First of all, thanks for this work. We used the information on the blog to basically optimize configuration and performance, based on, for LTP, and we found it extremely valuable. My question is, when you mention forward error correction, are you thinking of forward error correction at the LTP layer or somewhere else?
In our app we're trying, we actually have a bundle protocol application that has forward error correction.
So it would be like end-to-end forward error correction. Okay.
When we go to the advanced jumbos, the forward error correction would be actually encoded at the packet level. So the packet would be inflated in size a little bit to incorporate the forward error correction codes. When it's received at the destination link, it becomes decoded and becomes smaller again with the forward error correction correcting any error bits that might have occurred.
Okay, thank you.
I'm wondering, like you said that, like you can use this large segments when the data loss is small. It's like, I'm just wondering how small is small and what kind of number?
There was a lot of discussion about that on the IETF lists recently, and we're talking about less than 1%, by quite a bit less than 1% of packet loss. But I would refer to that study, and Eric, you may know about that study that was done. Jeff Houston was involved in a lot of that.
IPv6 packet loss? Fragment? You're talking about Jeff's IPv6 fragmentation?
This was a discussion thread on the IETF list, and I think it was the IPv6 list about what is the percent package loss in the average internet paths.
Oh, yeah.
Yeah. Right. And that's a big deciding factor about whether to use IP fragmentation or whether to use GSO GRO. If there's a lot of loss, you don't want to use fragmentation. If there's little loss, fragmentation is a good solution. Yes.
I was wondering for the fragmentation part, there's this SHIP protocol that has been standardized that besides compressing IP headers, it also fragments packets, and it follows the different acknowledgement modes with no acknowledgement, with acknowledgement only when there's an error. Is that possible to be applied in this context instead of?
Is it SDHC?
Yeah.
I know a very little bit about that. I've just really recently found out about it. It's using something that's fragmentation to a size of only 1280 bytes.
No, it's adaptable to any link layer technology. So you define profiles for the SHIP protocols,
Right.
Depending on what is below.
Right. We need to take a look at the comparison between the SHIP protocol and what I have is called Arrow and Omni, which do fragmentation at the IPv6 layer. SHIP protocol, what I understand, is using something that's below the IPv6 layer.
Should be below, but now that they have their own working group, it's being proposed also for upper layer. So it could be even a different layers, applied several times.
Right. We need to do a comparison between that protocol and my Arrow Omni protocol, where we have the IP fragmentation at the IPv6 layer, then the extended fragment header. But thanks for bringing that up.
Yeah, so I have the questions in the I think was it mentioned in the beginning of the presentation that it's they will be using the Solomon scheme for the error correction?
We have it, so we have kind of multiple layers. We have in the radio demodulation modulation pipeline that has Reed Solomon, but we also are going to try to enable a BP app that has fountain coding error correction.
What was the statement?
Fountain code?
Okay.
Yeah. A lot of this work was done by a company called Digital Fountain back about 10 or 15 years ago. And that provided the architecture for how to do forward error correction in the internet. And these are some coding schemes that can be used, Reed Solomon and the fountain code within that framework.
In like for your future error correcting for implementation, how many bits will you want your error correcting code to correct? Like how many, like what is the maximum number that you would like to correct?
I'm not an expert in that.
We did a little of looking, and I have to go back and think maybe a while for a paper go, but it depends. So you can get improved correction by how much redundancy you put in. So it kind of is a plot. And as you add redundancy, you kind of get bigger because for forward error correction, you're kind of appending a little bit to it. So you kind of end up with a plot of if you have more redundancy, you're going to have better error correction, but you're going to have a little bit more overhead.
So I think we need to move on.
Do you have one more?
What's your target round trip time for your week's work? Your round trip like delay?
We'd like to be able to use this on like Earth to Mars links where we've got 4 minutes and above round trip time. Okay.
Okay, good then. Thanks.